Section. Introduction. We've recently seen a technological revolution in the field of image synthesis, particularly with diffusion models. These models have not only made significant strides in image synthesis but have also greatly improved video synthesis. They can create highly realistic and diverse videos from a simple text prompt or even control the content and motion in videos based on different guidelines. However, there are still challenges to overcome, such as ensuring the coherence of semantics in both spatial and motion dimensions and maintaining the continuity of details in the videos produced. There are two main approaches to address these issues. The first approach uses multiple models to gradually enhance video quality, like the Imagine video method. However, these methods often optimize the same objective using the same inputs at each stage, without separating the tasks. This can lead to learning similar distributions at each stage and result in noticeable noise in the videos produced. The second approach requires additional guidance or training processes. While these methods have shown promise, meeting the guidance and training requirements in some scenarios can be challenging. Another common issue is the insufficient alignment of video-text pairs, which hinders further progress in video synthesis. To address these challenges, we've developed a method called I2VGen-XL, inspired by the success of SDXL. This method can generate high-definition videos with coherent spatial and motion dynamics and continuous details. I2VGen-XL first reduces the reliance on well-aligned text-video pairs by using a single static image as the primary condition. It consists of two stages, the base stage and the refinement stage. The base stage aims to ensure semantic coherence in the videos produced at a low resolution while preserving the content and identity information of the input images. To achieve this, we use two hierarchical encoders to extract high-level semantics and low-level details, which are then incorporated into a video diffusion model. The refinement stage improves the video resolution and refines details and artifacts in the videos produced. We've also collected 35 million high-quality single-shot videos and 6 billion images, covering a wide range of common categories in daily life, to enhance the diversity and robustness of I2VGen-XL. We've thoroughly evaluated I2VGen-XL using a wide range of data and compared it against current top-ranked methods. The results show that I2VGen-XL produces more reasonable and significant motions in these cases. Diffusion probabilistic models, DPM, is a powerful class of generative models used to learn a diffusion process that generates a target probability distribution. Initial efforts in image generation using DPMs were primarily focused on enhancing performance. These models have proven to be more effective than major traditional generation methods, such as GANs and VAE, in terms of diversity and realism. However, they are often inefficient. Some studies aim to reduce the number of denoising steps in the model by improving sampling efficiency. In the current mainstream of diffusion model-based image generation, language models are used to extract features and cross-attention is employed as a conditioning mechanism to control the generated content. Some methods aim to perform text-based image editing with diffusion models. In addition, another significant research branch is controllable generation, where additional conditions are used to generate target images in a more flexible manner. Early research in video generation primarily focused on using GAN-related methods, but maintaining spatio-temporal coherence as well as realism remains a significant challenge. Inspired by the significant advancements in image generation, diffusion models are also becoming mainstream techniques in video generation. Some models achieve significant performance improvement by designing a UNet with temporal awareness capability to directly generate complete video chunks. Controllability is also a crucial objective in the field of video generation. Some models utilize depth as an additional condition to decouple structure and content and achieve excellent results in video-to-video translation tasks. Others enable flexible control over video generation by combining textual conditions, spatial conditions, and temporal conditions. Generating high-definition videos has always been an important goal in this field, and significant progress has also been made recently. Some models synthesize high-definition videos to achieve performance improvement in a progressive manner. Compared to them, I2VGen-XL, as an alternative approach, focuses on enhancing the image-to-video task to enhance video quality, especially in the domain of video content creation, and jointly promotes the advancement of the community. Section Summary. The recent advancements in image synthesis have led to significant progress in video synthesis, but challenges remain in ensuring coherent semantics and maintaining continuity in generated videos. Existing approaches either optimize the same objective at each stage, resulting in noise, or require additional guidance and training. In response, we propose a cascaded method called I2VGen-XL that generates high-definition videos with coherent spatial and motion dynamics by utilizing a single static image as the primary condition and employing two stages: a base stage for semantic coherence and a refinement stage for improving resolution and refining details. We also collected a large dataset to enhance diversity and robustness. Section: I2VGen-XL. In this section, we'll be discussing our proposed model, I2VGen-XL, and how it enhances the quality and consistency of generated videos while maintaining the content of the input images. We'll start by giving a brief overview of the basic principles of the latent diffusion model. Then we'll dive into the specifics of I2VGen-XL, as illustrated in the figure. Lastly, we'll explain how the model is trained and how it works. The latent diffusion model, LDM, is an efficient model that gradually restores the target latent from Gaussian noise, preserving the visual manifold, and ultimately reconstructs high-quality images or videos from the latent. For a video, we use the encoder of a pre-trained VQGAN to compress it into a low-dimensional latent representation. The corresponding decoder can then map these latent representations back to the pixel space. The LDM consists of two processes: diffusion and denoising. During the diffusion stage, noise is gradually added to the latent representation to obtain a noise-corrupted latent. During the denoising stage, a denoising function is applied to the noise-corrupted latent. The optimized objective can be formulated as follows. The denoising function we use is inherited from the well-designed 3D net due to its powerful temporal modeling abilities. In this report, we will refer to LDM that utilizes a 3D architecture as VLDM unless otherwise specified. The goal of I2VGen-XL is to generate high-quality videos from static images. It aims to achieve two key objectives: semantic consistency, which involves accurately predicting the intent in the images and then generating precise motions while maintaining the content and structure of the input images, and high spatio-temporal coherence and clarity, which are fundamental attributes of a video and critical for ensuring the potential of video creation applications. To achieve these objectives, I2VGen-XL uses a two-stage strategy: a base stage and a refinement stage. In the base stage, we design the first stage at low resolutions, which primarily focuses on incorporating multi-level feature extraction, including high-level semantics and low-level details learning, on the input images to ensure intent comprehension and preserve content effectively. For high-level semantics learning, we use the visual encoder of CLIP to extract the semantic features. However, we found that this approach resulted in poor preservation of the content and structure of the input image in the generated videos. To address this issue, we incorporate an additional trainable global encoder to learn complementary features. Then, the two one-dimensional features are integrated via addition operation and embedded into each spatial layer of the 3D net using cross-attention. To mitigate the loss of details, we employ the features extracted from the encoder of VQGAN and directly add them to the input noise on the first frame. This choice is made based on the encoder's capability to fully reconstruct the original image, ensuring the preservation of all its details. In the refinement stage, we aim to enhance the video resolution and improve the spatio-temporal continuity and clarity of the video. To improve the video quality, we train a separate VLDM that specializes in high-quality, high-resolution data and employ a noising-denoising process on the generated videos from the first stage. Unlike the base model, the refinement model uses the user-provided simple text as a condition rather than the original input image. We found that introducing a different condition brings about effective compensation. Specifically, we encode the text using CLIP and embed it into the 3D net by cross-attention. Then, based on the pre-trained model from the base stage, we train a high-resolution model using carefully selected high-quality videos, all of which have resolutions greater than 1280 by 720 pixels. Section Summary. The proposed I2VGen-XL aims to generate high-quality videos from static images by achieving semantic consistency and high spatio-temporal coherence. It consists of two stages. The base stage focuses on intent comprehension and content preservation through multi-level feature extraction, while the refinement stage enhances video resolution and improves spatio-temporal continuity and clarity. The refinement model uses a separate VLDM specialized in high-quality, high-resolution data and incorporates user-provided text as a condition for effective video correction. Section: Training and Inference. Let's discuss the training and inference process of our model. We start by initializing the spatial component of our 3DU-Net model with pre-trained parameters from SD 2.1. This gives our model, I2VGen-XL, an initial ability to generate spatial data. During the training of the entire 3DU-Net, we control the parameter updates for the spatial layers by applying a coefficient, which we'll call gamma, set to 0.2. This is a scaled-down factor compared to that of the temporal layers. For the refinement model, we start with the well-trained base model and use the same training strategy. To focus the refinement model on spatio-temporal details, we train it specifically on the initial noise scales for denoising. We also use a two-stage training strategy. First, we conduct high-resolution training across the entire high-resolution dataset. Then, to further enhance the model's perception of details, we carry out a final round of fine-tuning on a carefully selected subset of around 1 million high-quality videos. During inference, we use a noising-denoising process to link the two parts of the model. We use DDIM and DPM Solver++, considering the generation efficiency and quality at different resolutions. After obtaining the low-resolution videos in the first stage, we resize them to 1280 by 720 pixels. We perform reverse computations with noise addition using DDIM on the new latent space. Then, we use the refinement model for the first denoising scales to obtain the final high-resolution videos. For our experiments, we use two types of training data: public datasets, which include WebVid10M and LAION400M, and private datasets consisting of video text pairs and image text pairs of the same type. In total, these two datasets consist of 35 million videos and 6 billion images, with resolutions ranging from 360p to 2K. We then sorted them based on aesthetic score, motion intensity, and proportion of the main subject. This helps us train with balanced samples. We use AtomW as the optimizer with a fixed learning rate of 0.00008. We simultaneously use dynamic frames and dynamic FPS during training. For frame length, we use a data supply ratio of 1:1, 1:5 for 1, 8, 16, and 32 frames respectively. Similarly, we use a ratio of 1:2, 4:1 for 1, 4, 8, and 16 FPS. We use center crop to compose the input videos with dimensions of 256 by 448 pixels and 720 by 1280 pixels for the base and refinement stages respectively. For training the diffusion models, we use the V-parameterization of diffusion models and offset noise with a strength of 0.1. The linear schedule is used. During inference, the default value of noise scales is set to 600, but it may vary for certain examples. To demonstrate the effectiveness of our proposed method, we compare the performance of I2VGen-XL with the leading methods Gen 2 and Pika. Our results show more realistic and diverse motions, such as the example of a flying dog. In contrast, the videos generated by Gen 2 and Pika appear to be closer to a static state, indicating that I2VGen-XL achieves a better richness of motions. However, our method loses some details of the input images. In our experiments, we also found that the degree of ID preservation and the intensity of motion exhibit a certain trade-off relationship. We strike a balance between these two factors. Our refinement model significantly enhances spatial details, including refined facial and bodily features, along with a noticeable reduction in noise within local details. The refinement model effectively preserves low-frequency data while exhibiting smoother variations in high-frequency data. From the perspective of the temporal dimension, there is a clear improvement in the continuity of the high-definition video. We also conducted experiments on a wider range of images, including categories such as human faces, 3D cartoons, anime, Chinese paintings, and small animals. The results show that the generated videos consider the content of the images and the aesthetics of the synthesized videos, while also exhibiting meaningful and accurate motions. Generating stable human body movements remains a major challenge in video synthesis. Therefore, we also specifically validated the robustness of I2VGen-XL on human body images. The model's predictions and generated motions for human bodies are reasonably realistic, with most of the characteristic features of human bodies well preserved. One of the main challenges in text-to-video synthesis currently is the collection of high-quality video text pairs. Therefore, Combining image synthesis techniques, such as stable diffusion and wanxiang, with image-to-video synthesis can help improve the quality of generated videos. Despite the significant improvements in both semantic consistency and spatio-temporal quality in video synthesis, our proposed I2VGen-XL still has some limitations. These include challenges in generating human body motion, limited ability to generate long videos, and limited user intent understanding. These limitations will serve as our future works.